Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to our 11th lecture of Business Math 1. In this lecture we will continue our chapter 5, which is basically about the linear applications and linear functions and the applications. In our previous lecture we have studied the definition of linear functions in one variable with the example of weekly salary function, the linear function in two variables, again with the example of weekly salary function, and generalizing we have seen the definition of linear function in n variables. Further, we have seen some applications of linear functions from the economic point of view. That is, what do we mean by the cost function, what do we mean by the revenue function and the profit function, and the linear cost function, linear revenue function and linear profit function. Mostly the examples we have seen were in one independent variable. Today we will continue with the examples of linear functions and we will see the break-even models. We start with some basic definitions. Depreciation is the cost allocated to any given period for a particular object. When organizations purchase an item, usually cost is allocated for the item over the period the item is used. For example, if a company purchases a truck costing $20,000 having a useful life of 5 years, then depreciation, that is the cost allocated to the truck for the given period of 5 years, will be $4,000 per year as a cost of owning a truck. That is, we have allocated $4,000 per year for the cost of truck. Now each major item purchased is recorded according to its current value or book value. For example, value of truck may appear on accounting statements as $20,000 at the time of purchase. So this will be the book value. But after 1 year, the price will be reduced to $16,000 and so on. In this case, depreciation can also be thought of as an amount by which the book value of an asset has decreased. So the book value in this case was $20,000 and after 1 year the book value was decreased to $16,000. Similarly, after 2 years the book value will decrease to $12,000 and so on, continuing up to 5 years. So this decrease in the value of an asset is mainly called as depreciation. What is straight line depreciation? Now straight line depreciation is one of the simplest method, and under this method the rate of depreciation is constant, which means that the decrease in the amount of an asset in every year will be the same as in the case of an example of a truck purchased. That is, every year the decrease in the amount of the truck will be $4,000. So the rate of depreciation is constant. So the book value declines as a linear function over time. If V equals the book value of an asset and T equals time in years measured from the purchase date for the previously mentioned truck, then V will be equals to function of time, and this is equals to purchase cost minus depreciation, which is equals to 20,000 minus 4,000 per year. So this is the book value of an asset in time t. Now if we plot v is the function of time, which is 20,000 minus 4,000 t, then we can see that here time t is the independent variable and v, which is the book value, is the dependent variable and time is the independent variable. If we write it in our proper slope intercept form, we obtain v is equals to minus 4,000 t plus 20,000, which means that the slope is negative. This minus 4,000 is basically tells us that, gives us the depreciation, which is by definition should be negative. That is, when time t is equals to 0, the book value was 20,000 and we obtain, this is our graph of depreciation, which is a straight line. Since the depreciation is negative, which is the slope here, the graph falls from left to right, and we can see that the slope is negative, which implies that the allocated value or the depreciation decreases with the passage of time t. So depreciation of any object is a linear function, is a straight line, always negative, and the book value of any function can be calculated in terms of time with the help of depreciation. Now we come to demand functions, linear demand function. A demand function is a mathematical relationship expressing the way in which the quantity demanded of an item varies with the price changed for it. The relationship between these two variables, that is the quantity demanded and the price per unit, is usually inverse. That is, a decrease in price results in an increase in demand. A very simple example is, if you increase the price of petrol, then the demand of the cars fueling the petrol will be less. If we decrease the price of petrol, then the demand will be more. So these two quantities, that is the demand and the price per unit, they are inversely proportional to each other. If we increase the price, the demand of that thing will be less. If we decrease the price, the demand of that object will be more in the market. But in some special cases, the demand function may be constant. For example, in the case of medicines, no matter how much high the price of the medicine is, the demand will be the same. So this is basically our demand function, depending upon the price and the quantity demanded. Most demand functions are non-linear, but there are situations in which the demand relationship either is linear or can be approximated by a linear function. Now, since the demand function is depending upon the price, so in this case price is the independent variable and the quantity demanded is dependent variable. If small q represents the quantity demanded, then it will be the function of price, that is, and if p represents the price, then small q will be equals to f of p, can be equals to 45,000 minus 75,000 p. So it is a linear function in terms of price per unit. And since we have said that these two variables, quantity and price, are inversely proportional to each other, so the graph in this case will be equals to, if the price is high, we know that price is the independent variable, it will show on the x-axis. Quantity is the quantity demanded, and price per unit. If the price will be high, the quantity demanded will be less, which means that they are inversely proportional to each other, and the graph of this linear demand function will have slope negative. As we can see from this particular example, that quantity is equals to 45,000 minus 75,000 p, where p is the price per unit, and here m, our slope is negative. That is, higher the price, lower the demand, lower the price, higher the demand. Here price is higher, the demand is lower. Here price is lower and the demand is higher. So the linear demand function can be expressed in terms of graphically in terms of a straight line, and is usually either a constant function or a line with negative slope, that is, line falling from left to right. Let us consider one more example of a function, that is the linear supply function. A linear supply function relates the market price to the quantities that suppliers are willing to produce or sell. Simply, what is brought to the market depends upon the price people are willing to pay. Now, in contrast to the demand function, the quantity which suppliers are willing to supply usually varies directly with the market price. Supply functions can also be approximated using linear functions. Now, if again Q is representing the quantity supplied and P is the price, then the relation will be equals to Q equals to function of price. That is, price is again the independent variable and the quantity supplied is the dependent variable. And the supply function says that the quantity is depending on the price directly. For example, assume that you own a fish board. Considering all the other factors being equal, how much incentive is there to sell the fishes if wholesale price is $100 per kg, and how much incentive is there if wholesale price is $350 per kg? Definitely, if the price is higher, as we have said that the supply function is directly proportional to the price, if the price is 100, then the quantity supplied will be more, that is Q will be more. In this case, if the wholesale price is 350, then the quantity will be Q of 100. In this case, we are given with the two prices. If the wholesale price is $100 per kg, the quantity supplied will be less as compared to if the wholesale price is $350 per kg. What will be the graph in this case of the supply function? The graph in this case is, if this is 100, this is 350, again price is on the x-axis, that is the independent variable, and the quantity supplied is on the y-axis, that is the dependent variable. When the price is $100, the quantity will be, let's say, here. When the price is 350, let's say the quantity supplied will be here. So this is basically a linear function with positive slope, that is the line is rising from left to right. More price means more quantity supplied, less price means less quantity supplied. This is the opposite of demand function. Okay. Now, using these two functions, we will see what do we mean by the market equilibrium. If we are given supply and demand functions of a product, then market equilibrium exists if there is a price at which the quantity demanded equals the quantity supplied. For example, suppose demand and supply functions have been estimated for two competing products. Okay. For example, if we have the demand function Q in terms of the prices of two products. We have two competing products, P1, P2 are the prices of the products, and if this is, let's say, equals to 100 minus 2 P1 plus 3 P2, here we would like to write it as demand function 1 and supply function 1. Quantity supplied is depending on the price P1, which is 2P1 minus 4. Again, some demand function depending on the product 2, $150 plus 4 P1 minus P2, and Q supply function 2 is depending only on the product P2, which is 3 P2 minus 6. Now we have the demand and supply functions for two competing products. That is, we have product 1, we have product 2. QD1 is the demand function of product 1. Product 1 and supply function product 1. Now the second set is the demand function and the supply function of product 2. Okay, now QD1 is the demand function of product 1 QS1 is the supply function of product 1 QD2 is the demand function of product 2 QS2 is the supply function of product 2. Okay, now we have few things to observe, that the demand and supply functions are linear. All these four functions, two functions of demand QD1, QD2, and two functions of supply QS1 and QS2, they are linear functions of the product 1 and product 2, and where P1 is the price of product 1, P2 is the price of product 2. All these four functions are linear in price P1 and P2. Second thing, what we can observe, that the quantity demanded of a given product, that is QD1 and QD2, depends on the price of the product and also on the price of the competing product. That is, QD1 and QD2 are depending on the price of both the products P1 and P2. QD1 is a function of the prices of both the products, prices P1 and P2, and QD2 is a function of the prices of both the products with prices P1 and P2. Third thing, what we have observed, that the quantity supplied of a product depends only on the price of that product. That is, QS1 is the quantity supplied function, QS2 is the quantity supplied function of product 2. They are only the functions depending on that product only. That is, QS1 is a function of product 1 only, and QS2 is a function of product 2 only. Now, when we will obtain our market equilibrium? Market equilibrium would exist in this two product marketplace if prices existed and were offered such that the demand function of product 1 is same as supply function of product 1, and the demand function of product 2 is same as the supply function of product 2. Okay, now what were the supply functions and demand functions of product 1? They were actually 100 minus 2P1 plus 3P2. This was the demand function, and the supply function was 2P1 minus 4. And we have said that the market equilibrium for this product would exist when the demand function is equal to the supply function. That is, when these two are equal. We can simplify this further by obtaining by adding and subtracting our prices P1 and P2. We obtain 4P1 plus 3P2 minus 4P1 plus 3P2 is equals to minus 104, or 4P1 minus 3P2 is equals to 104. So this is our equation of market equilibrium, linear equation in two variables, that is prices P1 and P2 for the two products, product 1 and product 2. Okay, now the market equilibrium for the product 2. It will exist when the demand function for the second product is equals to the supply function for the second product. Okay, so what were these functions? The demand function for the second product was 150 minus plus 4P1 minus P2, and the supply function was 3P2 minus 6. In order to find the market equilibrium, these two linear functions should be equal, that is 150 plus 4P1 minus P2 is equals to 3P2 minus 6. Simplifying, we obtain P1 4P1 minus 4P2 is equals to minus 156, or 4P2 minus 4P1 is equals to 156. Now we have two equations, equation B and equation A. Equation A was 4P1 minus 3P2 is equals to minus 3P2 is equals to 104. Now we have two equations A and B in two unknowns, prices P1 and P2. We can easily solve these two equations simultaneously to find the values of the prices P1 and P2. We can simply add them and we obtain P2 is equals to 260. Putting the value of P2 in any of the equations A and B, we obtain the value of P1 as 221, which means that the conclusion we have that if the products are priced accordingly, the quantities demanded and supplied will be equal for each product. So by using our demand function and supply function, we have obtained the situation where we can obtain the market equilibrium. So far we have seen two more examples of our linear functions, that is the demand function and the supply function, and with the help of these two examples we have solved the market equilibrium case, that is when the demand function is equals to the supply function and we can find the value of the price for which both the functions are equal or for which we can obtain the equilibrium. Now we come to our break-even models. Now, break-even models is a set of planning tools which can be useful in managing organizations. Break-even analysis focuses upon the profitability of a firm. In break-even analysis, we identify the level of operation or level of output that would result in a zero profit. The term zero profit we have already heard in our previous lecture when we were doing the question from our exercise. That is the situation when the linear profit equation is equals to 0. That is when the revenue function is equals to the cost function. So break-even analysis identifies the level of operation or level of output that would result in a zero profit. The level of operations or output is called the break-even point. Break-even point represents the level of operation at which total revenue equals total cost. That is, our P of X is our profit function in terms of X, which is the number of units sold and produced. This is only the difference of revenue function and the cost function. And break-even point represents the level of operation at which the total revenue equals total cost. That is our 0 point. When our profit is 0, that is when revenue is equals to the total cost. Basically, break-even models tells us about that at which point we can obtain the profit or at which point our firm will be in loss depending upon that particular product. So any changes from the level of operations will result in either a profit or a loss. Once we have found the break-even point at which we are obtaining the zero profit, then any changes from that value of break-even point will either result in the profit or loss. Now, break-even analysis is mostly used when firms are offering new products or services, evaluating the pros and cons of starting a new business. That is, at which value of the units sold or produced the firm will obtain the profit from that product. Or if a firm is offering a new service or new product, after how many units sold or how many units produced, the firm will start gaining the profit. To find the break-even point, main thing is we have to find our cost function. We should know our cost function, we should know our revenue function, and we can write our profit function in terms of cost function and revenue function. And from there we can find our break-even point. There are some assumptions in the case of cost function and the revenue function, because these are the two main functions playing role in giving us the break-even point. Now our total cost function and total revenue function are linear. For the total cost function, the assumptions are that the linear total cost function implies that variable cost per unit either are constant or can be assumed to be constant. That is, if we recall our cost function, which was C of X, as the sum of total variable cost and total fixed cost. Now, to find the break-even point, there are some assumptions. First assumption on the linear cost function is that the variable cost, that is this function, per unit either are constant or can be assumed to be constant. Okay. Now, total variable cost depend upon the level of operation or output, and fixed cost portion, that is this portion, is constant over the level of operation or output being considered. That is, for that operation, fixed cost will be treated as constant. There will be no change in the fixed cost for that period. What are the assumptions on the revenue function? Linear total revenue function assumes that the selling price per unit is constant. What is our revenue function? That R of X, where X is the number of quantity sold or produced, is equals to the price P into the quantity sold or produced. And we are assuming that the selling price per unit is constant. In case of non-constant selling price, average price is chosen for purposes of conducting the analysis. Variable cost per unit is less than the price per unit. This is very much clear from the definition of the profit function, which is the difference of cost function from the revenue function. And we are saying that variable cost per unit, that is this one, a part of this cost function, is less than price per unit. That is, R of X is greater than variable cost. And this makes sense because if the price per unit is less than the variable cost, then a firm or an organization will have loss all the time. That is, when this profit function will give us some negative value, and for every value of X, that is for every value of units produced and sold, a firm will have loss at the every time. Okay. So what is the main goal in break-even analysis? Is to determine the break-even point. That is the point at which the revenue function is equals to the cost function, or to obtain the zero profit. The break-even point may be expressed in terms of volume of output or level of activity, total dollars sale, or percentage of production capacity. For example, a firm will break even at 1000 units of output, that is the volume of output, option 1 is given, when total sales equal $2 million. That is, break-even point can be expressed in a combination of these three possibilities. Either we will be given the volume of output. Here in this case we know the volume, which is the 1000 units of output, or the total dollar sale. Here we know the total dollar sale equals 2 million, or when the firm is operating 60% of its plant capacity, or the percentage of production capacity. Knowing two things from these, we can find the break-even point. So what is the method to find the break-even point? The methods are straightforward, and there are alternative ways of determining it. The usual and the easiest approach is formulate the total cost function as a function of x, where x is again the number of units produced and sold, which will give us the level of output. Formulate the total revenue function as a function of x, and put C of x equals R of x, that is cost function equals the revenue function. The resulting value of x is the break-even level of output. Alternatively, we can put our profit function equals to 0 to find the value of x. That is, if we put our profit function equals to 0, again we obtain our third step, that is R of x equals cost function, and our break-even level of output is denoted by x with subscript capital B and E. Okay, now we come to an example. The example says that a group of engineers is interested in forming a company to produce smoke detectors. They have developed a design that variable cost per unit, including materials, labor, and marketing cost, are $22.5. Fixed cost associated with the formation, operation, management of the company, and purchase of the machinery cost $250,000. They estimate that the selling price will be $30 per detector. Now, we are asked to determine the number of smoke detectors which must be sold in order for the firm to break even on the venture. For this, first we will find our revenue function. Now, if x is equals to the number of smoke detectors produced and sold, then our total revenue function R of x will be equals to price, which is $30, into quantity. Then our revenue function will be equals to price, which is $30, into quantity, which is x. So this is basically our revenue function. Next step is to find the cost function, that is C of x. And C of x we know is the total, or is the sum of total variable cost plus total fixed cost. Okay, so our total fixed cost associated with the formation, operation, and so on cost $250,000. So our total fixed cost is $250,000, and our variable cost per unit, including material, labor, and marketing cost, are $22.5. So our cost function is 22.5x plus our total fixed cost. Okay, and we have to find our break-even point. That is our third step, when the revenue function is equals the cost function. Our revenue function is 30x and our cost function is 22.5x plus 250,000. Simplifying, we obtain 7.5x is equals to this, and solving for x we obtain 33,333.33 units sold or produced. So this is the value of x, which will give us our 0 point or break-even point. Okay, now here we have used our third point, that set r of x equals c of x. Now we will use our alternative method, that is put by putting our profit function equals to 0, which means that r of x minus c of x is equals to 0, which means 30x minus 22.5x minus this is equals to 0. Simplifying, 7.5x minus this is equals to 0, or 7.5x is equals to this. Further simplifying, we obtain the value of x, that is the number of units sold or produced, is 33,333.33 units, and we can see that the break-even point or the 0 point in both the cases is the same. Okay. Now we are further asked that preliminary marketing data indicate that the firm can expect to sell approximately 30,000 smoke detectors over the life of the project if the detectors are sold for $30 per unit. Determine expected profits at this level of output. We have our profit function, which is 7.5x minus 250,000. We are asked to find the level of output when x is equals to 30,000. So our P of 30,000 equals to 7.5 into 30,000 minus 250,000. Simplifying, we obtain this, and further we obtain minus 25,000. So this tells us that if the smoke detectors produced or sold are 30,000, the company will have a loss of 25,000. So now we have seen that with the help of our simple cost function and revenue function, we can find our profit function, and simply by putting our profit function equals to 0, that is r of x equals to c of x, we can obtain our break-even point or the 0 point. Now the graphical analysis of our break-even point. Here we have our revenue function R of x, which is this, and R of x is equals to 30x. So it is a straight line passing the origin. This is our 30x. Okay, this is our revenue function. Okay, now our cost function C of x, which is equals to 22.5x plus 250,000. Let's say this is equals to 250,000. Then in case of no unit x is equals to 0, our graph starts from here. So this is our cost function C of x, and we can see that 250,000 is basically our fixed cost. So this is our fixed cost, and this is our variable cost. This is our variable cost, and as x increases, this ratio of variable cost will remain the same. As x is smaller, this is small, x is in between, this is a bit more bigger. As x increases, our variable cost is also increasing, but this fixed cost is the same. Okay, now what do we mean graphically by our break-even analysis? That is, this was our revenue function, this is somewhere 250,000, and this is our cost function C of x. So now we have two straight lines, and we want to find the break-even point, that is graphically the point where both the lines intersect. So this is the point where both the lines intersect, that is the value of x, which is equals to 33,333.33 units. If we observe at our graph, clearly before the break-even point, that is on the left of our break-even point, the cost function is greater than the revenue function. So the firm will have a loss, because here C of x is greater than our revenue function. If we look at the right side of our break-even point, here the revenue function is greater than the cost function. So here a firm will have a profit. That is, before the break-even point, a firm will be in loss, and right after the break-even point, the firm will be in profit. So this is what do we mean graphically by our break-even point. Also, what is our profit function? P of x was 7.5x minus 250,000. Okay, when x is 0, the profit is minus 250,000. Let's say if this is equals to minus 250,000, then when profit is 0, this is our x, and it will cross the x-axis at the value of x equals to the break-even point. So we can also see from this profit graph that before the break-even point, the profit was negative means loss. After the break-even point, we have positive value, means here we have profit. And the break-even point is the point where our graph of profit function intersects the x-axis. In the case of revenue function and cost function, break-even point is the point where both the graphs intersect at the point. That is the common point of both of the graphs. And before the break-even point, the firm will have loss, and after the break-even point, the firm will have profit. So with this, we end our today's lecture by summarizing what we have done today. We have seen some examples of linear functions, some more examples. In terms of depreciation, the graph of depreciation, which is a straight line, demand function, which is usually linear, supply function, their graphs, and using the demand and supply function, we have studied the market equilibrium. Then, continuing further with the concept of market equilibrium, we have studied the break-even models. In the break-even models, we have seen the assumptions we need on our revenue function, cost function, the method to find the break-even point, and the graphical interpretation of the break-even point. With this, we end our today's lecture. Hope these terms were clear to you, and next time we will continue with our next lecture, which is about quadratic functions and applications. Allah Hafiz, students.